Hello, everybody, and welcome to this week's Green Bank Observatory Community Zoom. Just a few words about the status of the observatory and what's happening here. So GBO and NRAO had a nice presence at the IAU General Assembly in Cape Town, South Africa. A lot of people are on their way home, but by all accounts, it was an excellent meeting, and there was a lot of attention paid to Green Bank data while we were there. What's happening with the telescope? We're actually observing now. We're back on the air. We had a shutdown to work on some infrastructure needs. The foundation work has been completed. And what we did was replaced a large section of the foundation to replace the concrete. We had found that some of the concrete was degrading, and it was prudent to replace it all. We've replaced more than half of the concrete foundation now, or about half, and in the next year or two, we will finish that work. The good news is that the foundation looks great. The concrete work was well done. It's all tested, and the telescope is behaving beautifully. Next week, we will shut down again and replace several steel wear plates in the track. And then in a few weeks after that, we will be replacing some of the wheels, especially two wheels that are slightly damaged. And we plan to replace every wheel in the next several years. So this is all part of an ongoing infrastructure upgrade to make sure that the Green Bank telescope works well for the next decade or two or three. And I'm very grateful to the National Science Foundation for providing the funding for this long needed upgrade. Thank you for submitting your proposals. There were several outstanding proposals. These are now undergoing technical reviews and soon will be undergoing panel reviews. The disposition letters are scheduled to go out November 5th. So on November 5th, you will learn about the fate of your proposal. All right, that's all I have. I'll hand it over to Jay Lockman, who will introduce today's speaker.
Thanks, Jim. Today's speaker is Priya Bangale from the University of Delaware, and she's speaking on a 350 megahertz Green Bank telescope survey of unassociated Fermi-LAT sources. Let me remind everyone this session is being recorded for later viewing and will be up on our website probably within 24 hours, and that if you wish to submit questions, please use the Q&A box at the bottom of your screen. Take it away, Priya.
Hi, everyone. Thank you for inviting me here. And let me share my screen. Can you see my screen?
Yeah, yes.
Okay. So, hi, I'm Priya. I'm a postdoc at Unassociated of Delaware. And thanks, Jay, for inviting me. I'm very happy. So this project started when I was a master's student, and it was very exciting to come to Green Bank, and I came a few times for observations for this survey, and the place is absolutely beautiful. So I'm very excited to talk about this survey. So before going to the survey, let's talk about these exciting sources. So pulsars, these are highly magnetized, fast spinning, and very dense sources. So we can imagine them as the highly dense sources as density of a sun, and they are squeezed in together with the size of a small city, like a 10-kilometer. And because of their misaligned magnetic and rotation axis, we get a pulsed emission in the form of lighthouse manner. So whenever the beam is crossing our line of sight, we get a pulse, and then we combine these pulses and we get a form of integrated pulse, and that's our pulse profile. These forms after following a Korskova supernova. So these are very specialized sources, and they have a very, very precise period. They are most accurate clocks in the universe, and based on their periods, we have types of pulsars. So we have normal pulsars with the relatively slow period and relatively relatively marginalized magnetic field. Then we have millisecond pulsars. They are faster, less than 10 milliseconds, let's say, and they are higher magnetic field. And then magnetars, so even higher magnetic field as their name suggests, but they are slower pulsars. Now, in this talk, I will focus more on millisecond pulsars, and then I will let you know why I'm doing so. So there are subcategories of millisecond pulsars. So millisecond pulsars, they are basically type of recycled pulsars. They are binary systems initially. They accrete mass from their companion, and here is the artist's impression. So there are isolated systems. So we don't know exactly why isolated are formed, but one of the theory is they ablate their companion through the wind, and then when probably the companion gets very close to the pulsar. And then we have exotic systems, which is black widow and redback. So somehow pulsar astronomers really like the spiders, and that's why we have these names. So black widow pulsars, they have short orbital periods, and so the companion is having low companion mass, so less than zero point 0.1 solar masses and very tight orbit. And here in the picture on the right, it's actually the artist's impression for the black widow pulsar. And here we can see the pulsar is actually ablating its companion with its strong wind. And then we have another, and these black widows, they constitute around 10% of the millisecond pulsars. Then we have redback systems. They have heavier non-degenerate companions, so slightly heavier mass than black widow pulsars. And then they have also eclipsing companion. But the orbital period is slightly longer than orbital period could be similar to black widow. It's just the mass difference of the companion. Then we have eclipsing MSPs, where the companion eclipses for longer time, and then we have longer period binaries, where the binary period could be more than a day. So these are just the broad classification of type of MSPs. So before going to and discussing the survey, let me give you a little brief history about the idea of this survey. So let me take you back in time. So imagine when Fermi was launched, this is 2008, and then the survey started in 2009. And what information we had is like 16 pulsars were detected from the bright source list, and most of them were young pulsars, and 3 millisecond pulsars later discovered from Ransom et al. And from E-grid data, most of them were young pulsars. So what we know was like from this galactic field is like mostly either they are young pulsars, and we were not even sure if at gamma ray energies we will even find more pulsars. So all the picture was really unclear. Then Mallory Roberts came with an idea to search with Fermi catalog for faint sources for the unassociated source list. So this was really the first time searching for Fermi catalog for its faint sources. Before that, only the bright source list was searched for pulsars, and these were all unassociated sources, so we really don't know anything about it. So the expectation was that if we really find anything, it could be a combination of young pulsars and millisecond pulsars, might be. So here are our pointings. So we searched for 49 such sources, and these were to mention, these were 49 fainter Fermi sources, not the bright source from the bright source list. They were away from the galactic plane, as we can see here. And all previous GBT surveys, they were very long surveys, and all these Fermi pointings, they were 30 to 32 minutes only. So very comparatively very short pointing. So not lot of radio time was actually observed also. So these were radio time efficient. This was actually very radio time efficient survey. And let's go to the results. So this survey actually was quite successful, actually very successful, I must say. So we detected 18 millisecond pulsars in our survey, and 10 were actually quite unique to our survey. These were discoveries. 2 of them were known to our pointings. So, and 4 of these, bottom at this table, these are radio quiet discoveries. So among these 18s, eight of these are actually detected at 820 megahertz, because those were not very sensitive at 350 megahertz. And then we also, when we had detected at 820 megahertz, we also detected at 350 megahertz. So why 350 megahertz survey? Because we didn't know about the precise location from the Fermi pointing, Fermi look survey. These were unassociated surveys, so we needed a larger area region. So that's why we chose the 350 megahertz band. And we can see out of 49, we detected 24 pulsars in this survey. So this is some sort of definitely a record. This was definitely a groundbreaking survey. And story doesn't end here. Out of these 10 discoveries, we have 3 black widows, 2 redbacks, and 1 isolated pulsar. And we can see we have all MSPs, and these are the pulse profiles of all these MSPs. And that was the reason in the beginning I said, like, I will concentrate on MSPs in this talk. So this was really a big surprise from this survey, that we found all of those MSPs in these discoveries. And again, the story doesn't end there. Out of these 10 discoveries, we detected pulse camera emission from 9 of these MSPs. So very, very huge, actually huge success. And it was a very, very happy survey, actually. So again, this discovering pulsars is not actually enough. So you have to go for the timing solution. So you have to go for follow-up radio observations at different frequencies, and find the parameters, find all the pulsar properties, like precise period, precise how the period is changing with time, and also how the dispersion measure is, and if these what are the binary parameters of these pulsars. And then when you have a accurate phase connected solution, you go to Fermi-LAT data, and then you use this solution, and then you fold the Fermi-LAT data, and you get to the Fermi-LAT. If you get the Fermi-LAT detection, and as I said, like, we have 9 of them. One of the MSP, we don't have Fermi-LAT detection, because it was a chance coincidence that we detected this MSP, and we only have radio detection. So let's discuss these MSPs a little bit in detail. So let's begin with Black Widow MSPs. We have 3 of them. So 0023 and 1810, they were very bright pulsars, and we detected just in first 2 seconds of data, whereas 1124, it needed full 32 minutes. And 0023 and 1124, they have like 0.1 companion mass. 1110 is even more special case. But before going into more properties, let me explain these plots here. So all these plots, all 10 of these profiles, the one thing common here is, like, all these black curves here, these are gamma ray profiles, and all the color profiles here, they are from the radio GBT observations at different frequencies. And here for each of them, we can see, like, for instance, in case of 0023, we see a little frequency evolution in case from lower to higher, and for example, also in case of, for example, 1810, we see a little bit of frequency evolution too, and then there is a misalignment of the peaks and slight alignment of the peak, but the peak is also very broad. So these properties are also we can study when we just align these gamma ray and radio profiles. So these frequency evolution of the radio profiles, this could be a suggestion that these short orbit period binaries, they are playing, the companion is probably playing a role here. And then the 1810, we have the highest minimum companion mass in our discoveries, and which shows that it's probably a connection with redback system, which I will talk next. And then 1124 and 1810, they show signs of eclipses in their with their companion, but the 0023 doesn't, its companion doesn't show any eclipses. We also have follow-up X-ray observations, and which shows that the intrabinary shocks are heating their companion. So these are like these observations are also exciting about black widow MSPs because not many black widows were discovered before this survey. So you have to just explain everything, you have to imagine here going back to the 2009. So this was really like having 3 black widow MSPs discovered. It's like it was really a big number at that time. So then we have 2 redback MSPs, and as I mentioned before, they have heavier non-degenerate companions with slightly higher masses than black widow pulsars, and they have longer eclipse fractions. So we have 3 of them. So we can see that for 2215, the gamma ray profile and radio profiles, the peaks are matching. So probably the emission originates, at least one of them, peaks, profile peaks, they matches. So probably the emission originates from a similar region. And then we have also X-ray observations with XMM Newton, which shows the orbitally modulated light curve. And the high companion mass here with relatively low motion of period, which shows that redbacks are probably descendant from their intermass extra binary. And then also because of how the system of compact orbits and little bit higher mass, if they are precursors of black widow, and if the whole picture is actually connected. So these are like, we are still basically these systems are still new and we are still learning about them. These are still very exciting. Then the third type of binaries we found are longer period binaries. We have 3 of them. In 01, 02, we also have polarization measurements, and we found higher degree of linear polarization. And again, we have slight alignment of gamma ray and radio profiles here in case of 0307, and no X-ray detection in case of these. Now 1551, this is the unique MSP because this is the only MSP where there is no gamma ray detection. As I said, this was a chance detection as it was outside the Fermi error radius. And then we have short period binary 1302, and we have the only isolated MSP from our discovery, 10 discoveries, and the 0341 shows high degree of linear polarization, and the 1302 shows like brief eclipses. So I'm just listing here the special characteristics of each this pulsar, because each and every pulsar is actually quite unique in its nature. So, and again, there are no X-ray detection for these MSPs. So we have like all these number of pulsars, 10 new discoveries, 18 in total. So we have to discuss the population statistics now. So implications for the gamma ray pulsar population. So as I said, we have 18 MSPs now, and we have only 2 isolated. So from the sample of 10 new discoveries, we have only 1 isolated pulsar. So at the time of 2009, we had 25% known MSPs in the field which were isolated. Now, from the Fermi, particularly from the Fermi searches, we have total 91 MSPs known, and we have only about 18% isolated MSPs. So the fraction is lower now. And the most probably reason, this could be a radio selection effect, but also another interesting fact here is like we are finding more and more compact binaries now. So the fraction of compact binaries is increasing more and more. So this new 91 sample of 91 Fermi searches MSPs, 54% are actually compact binaries, and overall actually now 25% in the field are actually less than a day period. So this changes our understanding of the actually field of MSP population, like if the binary exchanges, if it's less important in the forming of these clusters, or if it's actually at all needed. And we also found in our survey that the isolated pulsars have actually a higher E dot than actually the binary pulsars. So and the speculation is actually isolated pulsars go through so much in their formation, and they go through spin down, and they could have actually lower E dot. So, but again, this could be a bias effect from our sample. So with less bias sample, we could actually see isolated pulsars have lower E dot. So to summarize, this work actually reports a groundbreaking survey. We have almost 50% success rate, and we have detection of 18 MSPs, and including discovery of 10 MSPs unique to our survey. And this survey suggests that majority of gamma ray sources at high latitude are either MSPs or relatively non-recycled pulsars. And previously, from Egret era, this was actually considered differently, which was more like young pulsars. And this also confirms that we had, as I said previously, a bias in favor of finding also isolated MSPs. Then we also saw that there is a dramatic pulse profile evolution with radio frequency, which suggests companion mass may influence the radio emission. And since not to the least, I must say that since 2009, the method of searching Fermi-LAT catalog and following it with radio observations, this method is very successful in finding pulsars, and many actually collaborations followed this method and successfully found pulsars through this method, and it actually still continues, and GBT also played a big role in this, and it's also is being followed with new instruments like FAST and MeerKAT to find even femto radio pulsars. So the search is going on, and there will be, I'm sure, many more pulsars will be found. So thank you.
Thank you very much. Excuse me. Thank you very much for a most interesting presentation. Let me remind everyone to submit your questions through the Q&A button on the bottom of the screen, and we already have some questions. Are there any follow-up studies to determine if any of these pulsars have optical counterparts?
They were actually performed, and they were presented in this paper, and for some of them actually, for 1810, I think there was an optical study done, and also I think for the 2215.
And I missed, are there companions visible in the optics? I mean, counterparts?
For 2215, the companion mass was measured in optical. So
Okay. Yeah. Here's another question. The high yield is remarkable compared to past Fermi unassociated source searches at low radio frequencies. Do you understand why?
because you need bigger error radius, we don't we don't know the precise location from the Fermi sources, so we need bigger error radius. That's the only reason.
So it really is the bigger beam of the GBT
Yeah.
low frequencies. Okay.
If we go to higher and higher radio frequency, we have smaller beam, and then we need precise location.
Okay, and one more question here. The Milky Way galactic center shows enhanced gamma ray emission, which could possibly be due to millisecond pulsars. Can you comment on finding millisecond pulsars near Sagittarius A star?
It is possible, but it is also difficult because of a very heavy background. So
okay, it's possible but difficult.
yeah, it's not easy.
Mm-hmm. Here's another question.
Also, Sagittarius A is a black hole, considered as black hole. I mean, so at Sagittarius A, not possible. Near Sagittarius A, possible.
Okay. Here's another question. What could be the reason for the offset in phase of the peak emission region in the pulse profile for radio to gamma rays?
Simple explanation, we don't know, because we don't understand the pulsar emission completely. But the possible explanation could be that the emission region of radio emission and gamma ray emission, they originates from the different places.
And just on this topic, what is the maximum phase difference seen in these pulsars between gamma ray, say, and radio?
Oh, I don't have the number for maximum, but from these, I mean, these profiles itself, we can see like they can be completely out of phase, and they can be completely on top of each other. So
yes.
So for example, 2215, they are like completely aligned, and in case of, let's say, 2129, they are completely out of phase. So
yeah. Well, that ends our open questions and brings us to the end of this week's webinar. Thank you very much.
Can I stop sharing my slides?
Well, you can just wait a minute because we'll terminate the session in just a moment. And just remind everyone that this has been recorded, and so within a day or so, you will be able to replay it on the Green Bank Observatory website. Please join us in 2 weeks for the next presentation in this series. Trey Wenger from University of Wisconsin will be speaking on cool diffuse ionized gas revealed by sensitive radio recombination line observations. We hope that you can join us then. Thank you and goodbye.